Okay, in this video, we're going to look at limits and continuity of several variables. So we're going to talk about what it means to say the limit as xy approaches ab of f of xy equals L. Intuitively, it means these function values can be made arbitrarily close to L, that means within epsilon units of L, by picking xy sufficiently close to AB, that means within delta units of AB. So more formally, you could say for any epsilon, there is a delta, so that if xy is within delta units of AB, that's what this says, then the f of xy is within epsilon units of L. That's what this says. So graphically, what's going on here is for any epsilon, there corresponds a delta, so that if xy is within this circle of radius delta around AB, then f of xy will be within this interval around L. Another way to say it would be for any epsilon around L, you could make all the f of xy's in that interval around L by finding a delta interval around AB, so that if any xy is in this circle on the xy plane, then f of xy will be within epsilon units of L. There you go. Now, the only catch is, well, what makes this very different from Math 151, in Math 151, x had to approach a from the left and right. But here we're talking about x and y approaching the point AB. There's infinitely many ways you can get there. So unfortunately, all the possible paths would have to give you the same limit. If you can find two different paths to that point AB and get two different values for your limit, then the limit doesn't exist. In other words, it's a lot easier to show that a limit doesn't exist. If you can come up with two different pathways to that point, AB, and you get two different limits, the limit does not exist. For example, for this one, we're getting close to 0, 0. So there's lots of ways that you can get close to 0, 0. Along the x-axis, when y is 0, you get x squared over x squared. And as x0 gets close to 0, 0, this, you get 1. Along the y-axis, when x is 0, this drops out, but you get negative y squared over y squared. And this is getting close to negative 1. So therefore, the limit does not exist. Here's another one. If we get close to 0, 0 along the x-axis, y equals 0, the top is 0, the bottom is x squared, so this is getting close to 0. But along the line y equals x, you would have x squared on top, and this becomes x squared plus x squared, which is 2x squared on the bottom. This limits 1/2. So graphically, what's going on there, if you come in along the x-axis, the z values, the f of x, y's are all going to be 0. But if you come in along the line y equal x, which is right here, the z values are getting close to 1/2. So whenever you have a surface that has a ridge like this, or you can think of it as a cliff, that's when you have a case where the limit does not exist. Well, that's one possible way a limit does not exist. So the question would be, how do you know what paths to try? Well, you're trying to pick a path so that the expression simplifies, okay? Now, the common ones are the x and y axis, y equals x squared, x equals y squared. You see what happens if you pick x equals y squared? The top becomes y to the fourth, and the bottom becomes y to the fourth plus y to the fourth, which is 2y to the fourth. So as this approaches 0, 0, this expression becomes y to the fourth over 2y to the fourth, so the limit's 1/2. Now, if you come in along the x-axis, the numerator is 0. And so this would be 0 over x squared, which is 0. What's going on there? If you come in along the function x equals y squared, you're getting close to 1/2 here at 0, 0. But if you're coming along the x-axis, the z values are all 0. So the limit doesn't exist. Here's an example of how you would show that a limit does exist. First of all, if you don't know if it exists or not, you should probably try several paths. And if you're getting the same value for your function value, for the limit, then you might think that perhaps it does. The squeeze theorem is a nice choice for certain problems. I'm going to show that the absolute value of this is getting close to 0 as xy gets close to 0, 0. And since the absolute value gets close to 0, the function gets close to 0 as well. First of all, 0 is less than or equal to the absolute value of this. And then you could break the absolute value up like this. And the trick is this expression right here is less than or equal to 1 because the bottom is bigger than the top. So you can say this is less or equal to 3 absolute value of y. This goes to 0, and this goes to 0. So by the squeeze theorem, the absolute value goes to 0. And since the absolute value goes to 0, so does the function. You could also, if you look at the book, you can actually use the formal definition on this one as well. So putting that together, a function is continuous at a point means three things. First of all, it has to be defined there. Secondly, the limit has to exist. We just talked about that. And thirdly, the two have to be equal, right? So let's look at some examples of that. There's lots of homework problems we're going to look at, but I'm not going to do all of them. I'll do a couple, and then I'll just let you hit the pause button, and you can see the other ones, okay? Anyway, but before we do that, a polynomial function is continuous everywhere in the xy plane. A rational function is continuous everywhere except possibly where the bottom is 0, right? So keep that in mind. So if you wanted, if they ask a question, where is this function continuous, you would say everywhere except it's not defined at 0 because it's not defined there, period. So that's enough to show that it's not a continuous function there. However, as long as we're here, we also showed earlier that the limit also doesn't exist. So this actually fails all three conditions. The function's not defined there, the limit doesn't exist, and obviously they're not equal. So if the question is, where is this continuous, you'd say everywhere except 0, 0, and that's one way you can write it. So here's an example where this function is defined at 0, 0. In fact, this is a piecewise function. It's defined to be 0 at 0, 0. So it satisfies the condition 1 of continuity. Does the limit exist, however? We actually proved earlier that this limit does not exist. So this satisfies condition 1, fails condition 2, and then therefore it fails condition 3. So where is it continuous? Everywhere except 0, 0. This one, however, let's take a look. This one is defined as 0, 0. It's defined to be 0, so it satisfies condition 1. And the limit exists. We just got through showing the limit was 0 because of the squeeze theorem. So this satisfies condition 2. And furthermore, it satisfies condition 3. Now, how would it satisfy 1 and 2 but not 3? Well, what if I define it to be 1 at 0, 0? If I defined it to be 1 there, it would satisfy condition 1. It would satisfy condition 2, but the limit would be 0, but they wouldn't be equal. So if I define it to be 1 there, it would satisfy 1 and 2, but not 3. Anyway, so like I said, there's lots of problems here. I don't have time to go over every single one. Let me do a couple of these. First of all, number 5, where does the limit exist? The limit exists everywhere because it's a polynomial function. That's all you need to say. So what is the limit? The limit, you can access that by plugging in the value 3, 2. For number 6, this function is continuous everywhere except where the bottom is 0, right? So it is continuous at 2, -1, and therefore the limit exists. We're actually trying to show that the limit exists here. But since it's a continuous function at 2, -1, you can go through and just plug in the value there, 2 for x and -1 for y, and get the answer there. Let's see. I'll let you look at the rest of these, 9 and 10. Okay, I'll hit the pause button, and you can check these out on your own. Same is true here. I'll do number 20, but I'll let you guys hit the pause button for 18 and 19, and then I'll go over number 20 with you. So for number 20, we're looking at this. We're looking at this limit. This is a function of 3 variables, right? I'm going to pick 2 paths and show that you don't get the same thing. One path is along y equals 0. If y equals 0, the numerator is 0, so the limit is 0. But along the path y, 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 you could say x, x, x also. Along y, 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 when everything equals y, you would get y squared plus y squared, which is 2y squared on the top, and you get y squared plus y squared plus y squared, which is 3y squared on the bottom, and this will equal 2/3. So I found two paths where they're not equal, so therefore the limit doesn't exist. Same is true here. I'll let you look at 29 and 30 and 31, and then I'll all right, here's 29 and 30, and here's 31. I'll look at 34. 34. They just want you to find the domain. So what would you do? This is going to be this is going to be defined everywhere except where what's inside is negative. What's inside has to be positive. That's what I'm trying to say. So if this has to be greater than 0, that means y has to be less than x plus 1. So the domain would be the region in the xy plane that's below this line, y equals x plus 1. It does not equal the line, right? It's a dotted line. Okay, almost done. I'll do 37, and you can do 38 on your own. So in 37, we want to know where is it continuous. So remember, there's 3 steps to this. It's going to be continuous except possibly at 0, 0. However, it is defined there, right? It is defined there. It's defined to be 1. Now, what is the limit? I'm going to show by the squeeze theorem that this limit is 0. How would you show that? Well, 0 is less than the absolute value of this, which can be written like this. I can break off the y cubed. Same idea. This is less than or equal to this, because this has a bigger denominator. So that this becomes 1/2. So this goes to 0. The limit of this is equal to 0. So therefore, by the squeeze theorem, the limit is xy goes to 0, 0 is actually 0, which does not equal 1. So this actually satisfies condition 1. Oops. This is wrong. It satisfies, it does not equal this, so it's continuous on R2 minus 0, 0, right? It's not continuous at 0 because this is a good case where it's defined and the limit exists, but they're not equal, right? Okay, I'll let you look at this one. Look at number 37. 37 is this function right here. I'm sorry, 38. I'll let you do this on your own. Hit the pause button. Last one. This is kind of nice. Sometimes you can use polar coordinates to help you compute limits as well. The key is, for this limit here, if you let x equal r cosine theta and y equals r sine theta, this is the important part. As xy is getting close to 0, 0, doesn't that mean the radius is getting close to 0? We don't care what theta is happening to theta. It's the r value that has to get close to 0. So if you make your substitution here, you get an r squared, because remember x squared plus y squared is r squared. You get this on the top. So when you factor out the r cubed, you cancel it, and now this, no matter what theta is, if this goes to 0, the whole thing gets close to 0. So that's a nice way to show the limit equals 0. For number 40, I'll let you guys do this on your own. All right, so here's the problem right here, and I'll let you guys look at this. All right, I'll talk to you guys later. Bye-bye.